In this video, we're going to think carefully about one idea, limits. By the end, I hope this idea feels simpler and more connected. In single variable calculus, we say the limit exists if a function gives the same value or the same y value no matter what direction we are approaching from. Whether we approach from the left side or from the right side, and if they give the same value, then we say the limit exists. Otherwise, the limit doesn't exist. So let me show you briefly. So on the xy plane, x and y, there's a function like this, and y equals f of x. And let's say we're interested in this point, like 5, 4. As you can see, when we approach from the left side, it gives the y value 5. And even if you approach from the right side, it still gives the same value, which is 5. So this is when we say the limit exists. If they don't give the same value, then the limit doesn't exist and it doesn't make sense. So it is purely about behavior near the point. What about differentiability? I hope you guys kind of remember what differentiability was. So basically, it is asking us one thing: does the function have a well-defined slope at this point? So let's say here, the same point. Do you think we can draw a one unique tangent line? I think yes, right? I think so. At this point, it's like roughly just horizontal. So the tangent line should be like this. So geometrically, it is asking, can we draw one unique tangent line at this point? This is about differentiability. That being said, if the function has a cusp or a short sharp corner or a vertical tangent or anything like jump, then it is not differentiable. For example, like here, you can see there's a sharp corner, right? Then it's not differentiable because the tangent line, we can draw a tangent line in multiple directions. Tangent line could be like this, or like this, or like this. There's no just one unique tangent line, so it is not differentiable. It still has a limit. The limit exists at this point, but it is not differentiable. So you need to keep that in mind, that if a function is differentiable, then it guarantees that it is continuous. However, it doesn't make sense in other way around. If a function is continuous, it doesn't necessarily mean it is differentiable. It is so important to remember this concept. It is so fundamental in calculus when it comes to limits. Now, let's talk about the same topics, limits and differentiability, but in multivariable calculus perspective. Let's talk about limits. Imagine you are in three-dimension space. So, z direction, x direction, and y direction. X, y, z. So you're in three-dimension space, and there's a point like this. Now we are interested in finding whether the limit exists or not at this point, the orange. Let's say A, B. What do you think? How can we find it? I assume it is, you can tell that it's not enough to just approach from the left and from the right side to prove whether the limit exists or not. So just intuitively, we can see that there are infinitely many ways to approach this point. So unfortunately, it is true that it gets a bit more complicated to to find whether the limit exists or not. However, the fundamental idea of finding the limit is still the same in multivariable calculus. So, so as you can see, you can just approach this point just like this, just straight, or kind of move around near the point and approach it, or like zigzags or whatever you want and approach it. So there are infinitely many ways to approach, and there are two ways to see whether the limit exists or not. So first, to show the limit doesn't exist, you just need to show two different limits on two different paths. Does that make sense? For me, it makes sense. Yeah. You just need to show the final height or z values is not the same from two different directions. Yeah, that's it. And number two, to show the limit exists in 3 dimensions, then you need to show that the limit is always the same regardless of the path you choose. So it's more trickier to use the latter one. The first one is mostly useful in multiple variable situations. But anyway, the fundamental idea is still the same. I wanted to show you that the core idea is not different. What about differentiability in multivariable calculus? In single variable, differentiability means whether we can draw one unique tangent line or not at the point, right? But in multivariable, it now is asking us, can the surface be approximated by a plane near the point? So instead of finding a tangent line, we are interested in finding a tangent plane. So differentiable means the surface looks flat locally. Let me draw, for example, in XYZ space. XYZ, and let's say there's a like a 3D object, and we are interested in like this point. You can kind of see the slope in any direction at this point here. It's well defined. That's when partial derivatives comes in, but we haven't learned it yet. So I just wanted to keep this just simple. So the slope is well defined at this point in any direction. So the surface looks flat at this point. So if we keep zooming in more and more, it looks like a plane. So I don't think I can draw it well, but it should be more like yeah, it's not well drawing, but there should be like a tangent plane at this point. So this plane is tilted like corresponding to the slope of this point. Today we explored limits and differentiability in multivariable calculus. Limits are really the foundation of everything in calculus. In single variable, it tells us how a function behaves as we approach a point. And in multiple variables, they tell us whether a surface behaves consistently in every direction. Once we understand limits, now we can start asking the next question. How does a function change in each direction? And that's what exactly partial derivatives are about, and that's what we will talk about next. Until then, let's keep things simply connected. Thank you.